All right. Yes. So the idea is to create a model. We should be able to look at a model. We should be able to assess the model by moving certain elements. So I actually showed you the actual device we are talking about. We are using the concept and the principles to actually explain how the whole photogrammetric process is done. Are you okay? Now we said there are different types of stereo restitution instruments or plotters, what we call the plotter. And so we have the direct optical, mechanical optical, we have analytical, and we have digital plotters. So their mode of operation actually tells us what, the name to give to it. Or we can also look at it in terms of rigorous or approximate solution instruments. So if it's rigorous, then it's more accurate. And then if it is approximate instrument, then we are talking about something like the stereoscope. I don't know, the stereoscope was we touched on that in photogrammetry 1, the stereoscope. Okay, so stereoscope was some kind of instrument with some mirrors and then binoculars that allowed us to place two photographs, align them along the flight line, and then we could then observe in 3D the two images now fused together, and then it created an impression, the 3D impression of the ground or the project area. Okay, so necessarily we needed some kind of stereo pair to photograph an overlap region, a common overlap region. And so the common overlap region then allowed us, by rearranging it, the photographs, left photograph, right photograph, we were then able to see, in 3D. And then I told you now that 3D coordinates are important for everything that we need it for modeling, for knowing what is actually happening on the ground. Okay, so that is recapping. That is what we talked about last week, and more. Talked about the advantage and disadvantage of using the optical, mechanical instruments. Are you okay? The format, the light source. Are you okay? Vapor mercury lamps were used as light source, and very, very interesting. Can you see the photograph on the screen? I think that this photograph was used in Photogrammetry 1. I don't know if you still remember this. Did you do the assignment? I don't want to go there. So don't give me an answer, please. Don't, revisit. Sometimes you are given an assignment and you don't do it, isn't it? But then I don't want to talk about it. But this photograph has actually been used before. Okay, so it's actually a photograph that is vertical. So we have different types of photographs. Okay, this one is the vertical photograph. We need 2 of them. Okay, so this is like, we have about 3 different types of photographs like this that we used. Okay, so I just put this here just to bring our minds to I need to mute now as fast as possible. So we needed to appreciate these things, that we are trying to map this area. We are trying to extract not just the planimetric, but then the 3D. We can see the buildings seem to be rising and all that. Okay, so compressing everything into 2D is not really an option for us at all. Okay, and hence the need. Are you looking at the photograph? Maybe you are not. Yes. Maybe you are now doing, I don't know, I wasn't sharing it properly. But you can see that the idea is to map the ground. This is black and white, but it could have been colored. Okay, the idea is to map the ground and get the XY coordinate of the objects of interest. And you can imagine that there are infinite number of points that can be collected from this project area. And normally, so a photogrammetric survey or any survey should allow us to obtain the three-dimensional coordinates for the particular area of interest. And hence, the need to understand the 3D process. We talked about a floating mark, IOK, which is actually created by, two marks, half marks, IOK, which are actually etched on clear glass, and then when they are separated, they tend to rise or fall onto the surface, the 3D surface. I mean, you have to have imagination, IOK, to appreciate what I'm talking about. And so we touched on that as well. We touched on the anaglyph method as a method of separation of images. Okay, so we wanted to, bring our attention to the fact that all we need to see in 3D is to separate the left view, the left photograph from the right photograph, and then we will create a 3D. And if we had two images that were fused but colored differently, blue and red, for example, we could separate them by wearing red and blue glasses. That separated the images, okay, so that in our brain, we get it all fused back again. We still are able to create a 3D model. And I had this, I had a 3D glass, the anaglyph glasses in my office some time back. It's cool, but I don't know, they've disappeared. Maybe they are still there, we can look for it. And so the frequency of the red and the blue color, we touched on that, etc. This is actually the mechanical instrument schematic diagram showing how the light is, illuminates the diapositive. You see here, we have the left diapositive and the right diapositive. And then we have to have a way of actually looking at the model through the binoculars. Are you okay? And then what the space rods are doing is that they are actually pointing to a particular part of the diapositive, okay? So that it's not like we are illuminating everything. So but light is collected and then brought into a certain focus. You can just imagine how such a system will work. But I actually showed now the real thing. It looks very gigantic and monstrous. Are you okay? But the whole idea was that recreate whatever happened on the ground in the office using these plotters. All right, and then we came to the conclusion that it's very important to find a way of checking, if you like, calibrating the instrument, the plotter. Every instrument in any type of survey needs to be what? Calibrated or checked. We need to find a way of checking. And one of the first things to do is to check the zero position. I think we talked about that. Omega phi kappa bx by bz is actually the B there actually stands for the base. So base x, base y, base z. Are you okay? And I hope you remember what the base is, the air base. So here, this we are referring to the model base. Are you okay? So there are three types of bases. The photo base, we have the air, we have the model base, then we have the air base. Okay, I'm just reminding you. I'm sure we've talked about it, but if you've forgotten it, then I think we all have to remind ourselves. So the photo base is actually denoted by small b, the air base by b, the model base. Okay, so we can use another symbol for that. But basically, so when you see bx, by, bz, then you are actually referring to the x component of the air base, and the air base really is the separation between what I've gone for this whiteboard. That's not what I really wanted. Okay, let me see. Try and share something else. The separation between the exposure station, the consecutive exposure stations. Okay, Where's my whiteboard? It's gone somewhere. Let me see. Okay. Preset whiteboard. Okay, let's go for this and see. All right. So if you have this, I'm reminding you again that between here and here, so exposure station 1, exposure station 2. Okay, this is the B. Okay, so that is the air base. Assuming if it's a plane, once I put the platform here, the platform could be helicopter or drone or whatever. Then this becomes B. When I replace this with the plotter, okay, the projector, yeah, plotter projector. Then in that case, this becomes the model base. B becomes the model base. Okay. And so on and so forth. If I look at it in terms of the photographs alone, then B becomes small b, and then that will be the photo base. Okay, so that will become the photo base. So you need to understand, please, if you don't understand, you need to halt, pause, try to understand it. The lecture is about understanding. Otherwise, this is a total waste of your time. So if you don't understand what I'm talking about, photo base, model base, try to, you know, get it, or just tell yourself, I'll find out, because we will have to understand it. So bx1, by1, bz1 now makes a lot of sense. So an equation like this, which is actually representing what we call the projective transformation. Now, let me remind you, the projective transformation is different from the orthogonal transformation. Are you okay? So a projective transformation is where the light is coming from one source. Are you okay? You see the way our light in terms of photogrammetry seem to all emanate from one point. Are you okay? All the light in photogrammetry seems to emanate from here. So we are trying to really get a bundle of light rays coming from the ground like this. Okay, so this one is a projective transformation. Projective transformation. Okay, as opposed to the orthogonal transformation, this one was using cartography, okay, where we project light in an orthogonal fashion, 90 degrees. The light is kind of making 90 degrees. So this orthogonal projection. So when someone says projective transformation, you should quickly start thinking that, okay, the opposite of that is what? Orthogonal. I'm not spelling it well. Are you okay? But then you should know that it's ORT, you know what I'm saying, yeah? ORTHOGONAL. Okay? Orthogonal. This is also used in technical drawing. Okay, so please let's understand that the equation there that you've seen here is actually referring to such a transformation where x0, y0 are the coordinates of the exposure station. Okay, the coordinates of the exposure station, which later on we actually going to give a name to it. Is that okay? X0, y0, omega naught, yeah, and say kappa naught. These actually represent, you know, the so-called coordinates that we are supposed to determine. Are you okay? In the so-called exterior orientation parameters. So x0, yeah, y0, z0. These are the exterior orientation parameters. Then omega, I can't draw omega, I can't write omega now, so I'll just type it. Omega phi, kappa, all of them not. Are you okay? So kappa naught, phi naught, and then omega naught. These are actually coordinates and orientations of there's particular exposure. Are you okay? When the airplane freezes, when you freeze the airplane at a point, and then we try to find out what are the coordinates at this point where we just took the picture. That will be S naught, Y naught, Z naught. So that's what you are looking at in this equation. Are you okay? All right. And then X, Y, Z. No, you can't have X, Y, Z. The reason we don't have in the smaller Z is because these are the X, Y are the photo coordinates. And then the A11, A12, A13, these are the parameters that we need to solve for. Are you okay? So in fact, in photogrammetry 2, it's all about determining these unknown parameters. Are you okay? We have the unknown parameters. Then we have, of course, these coefficients. Okay, so we need to determine the coefficients, put them in an equation, and then solve for them. Okay, so the C orientation parameters, they are all factored into this. And as part of our checking of whether the instrument is okay or not, we need to check on the accuracy with which it does this so-called projective transformation. The third one is the faithfulness with which the instrument is able to generate a model of the surface. Are you okay? The instrument's ability to generate an undistorted model. So now you can create a model which is distorted. So we try to avoid that as the third step. Then we have the determination of the instrument coordinates of the perspective center. Are you okay? So perspective center. Remember, I've just talked about S naught, Y naught, Z naught, okay, plus omega naught, phi naught, yeah, and then kappa naught. All right. So we carry out these tests using what we call the Rizzo plate. Rizzo is a French word, okay. So we kind of like place a glass, mark about 9 points on the glass, and then see how they will transform after we have carried out a projective transmission. In other words, after we have actually switched on the illuminate the light source and we have projected everything on the diapositive onto the model, we're supposed to now check if the equation up here will work. Are you okay? And then when we are doing that, the result plates, yeah, the clear glass with 9 points on them, that will bring you to more equations. Is okay. And I've put this here to explain to you that this is used also in remote sensing. Okay, the same process is used in remote sensing. Is that okay? All right. Now there's something I think we are missing here. The crosses that are marked on the clear glass, okay, is what is being described up here. Okay, they can be seen as fiducials, but remember that we talk about the fiducial marks in photogrammetry, in an area photograph, in a vertical photograph. Then the fiducials are actually corner fiducials and side fiducials. So, but then we can generically use the word fiducial in photogrammetry without worrying too much. Okay, so moving forward, we should be able to do the fifth test, which is also space resection. It should be possible to carry out space resection. So this equation is very simple. Okay, relate any ground coordinate for points A, B, and C with their the actual perspective center coordinates, X naught, Y naught, Z naught. Should be able to relate them. Okay, so in that case, this is the ground. Up here, we have, the perspective center. We have this ground point B with this coordinates, and then we have X, the other point A. So point B seems a bit higher than point A, etc. But then we can write an equation that kind of explains everything that we've seen here on the board. That is space resection. Is that okay? It's called space resection. We can also write it in matrix format. Is that okay? The same set of equations. Okay. And then even looking at it more in terms of geometry, we can actually look at the 9 result points. Okay, so result points that are actually on the plate are projected onto the model as points 1, 1, 1, 2, 1, 3, 2, 1, 2, 2. So 2, 2 seems to be a point in the center of the plate. So the plate is actually mounted up here, okay, in the photo plane, and then the projection plane. So you can imagine why we are having projection plane now, okay, and then we can carry on and write a few relationships, okay, between, you know, the minimum point in the model, the maximum point in the model, the focal length, etc., or the principal distance. We talk about the difference between the focal length and the principal distance very soon. So we can write these relationships. And then finally, before we finish up with last week's material, we can do the monograde test and the stereograde test. Is that okay? All right. So the monograde test, the difference between the monograde test and the stereograde test is that one of them takes just a single photograph and looks at the geometry. One of them, and the other one looks at what? 2 photographs forming a model. Is that okay? So the first one is to actually appreciate everything that you're looking at here will be familiar to you when you actually start doing some adjustments. In adjustment of coordinates, are you okay? We try to look at the unknown values, the residuals, the errors. Are you okay? And then we try to write an equation for it. So don't be scared by what you're looking at. This is just an observation of a coordinate xi, okay? So which means that I represents all the possible points at which we can collect xy coordinates. When this Zoom meeting, attention everyone, when this Zoom meeting ends, I want you to use the same link, and then we'll continue for another 30 minutes or so. Is that okay? Then we close. All right. So we have this relationship here, f over z naught. This more like a scaling is going on there. Are you okay? F over z naught is more like f over h, okay, which is the scale. And then now we can now transform one coordinate to the other. Are you okay? In terms of x and in terms of y, we can do that. Then of course Vx, like I said, V is the residual, X is the error, and the difference between the two coordinates, are you okay, is composed of the error and the residual. So this is actually the survey adjustment concept. What I'm talking about now is like teaching you survey adjustment. Okay, and then here we have the error propagation. I don't know if you've done a topic called error propagation. You can see that we shall now look at a differential version of omega phi kappa, smaller versions of it, that actually contribute to the error in x and the error in y. Okay, so the contribution of the rotational elements, which is del kappa, del phi, del omega, will now sum up, okay, to give you the total error in y and the total error in x. So this is the story. To cut a long story short, we should be able to relate the rotational elements, the errors in them, in this monograde test, yeah, relate that with the actual xy coordinates. All right. So bear with me and forgive me for introducing something that you probably not done or done. I don't know if you've done survey adjustment, but some of the concepts are being brought in. So in the stereograde test, the difference between the stereograde tests is that we now introduce, you know, a z component. I mean, and we also look at a common rotation of the model. Okay, so the monograde test doesn't look at the model, but the stereograde test look at the model. So when you look down here in this equation, okay, then you realize that we are actually trying to measure what we call the common phi and the common omega. So this one here is the omega, this is the phi, common omega, okay, and then there should be a way to actually relate all the points. Okay, so when you see ID, JD, then you're referring to, for example, 1, 1, 1, 2, as we saw earlier on. So I, comma J, it's synonymous with saying 1, 2, 2, 2, 3, 3. So it's referring to a set of points, IJ. Okay, all right. So as you can see in here, Then the ith and the jth point, okay, has reduced coordinates id and then jd, where d is the format. Format is like the dimension of the photo. Is that okay? All right. So in this test, we try to associate, the errors also in the z component. Are you okay? We relate it as appropriate. Are you okay? So the residual and the error makes up the difference in what we should have and what, so the unknown and the true value. So these are things that you learn in survey adjustment, which I think you started or you probably done an introduction to it. All right, so you see normal equations are coming in there. Is that okay? And so, yeah, this is something that we need to do as part of checking our instrument. Is that okay? All right, so that we have very good values. So if the instrument cannot be tested for this, checking of common omega, common phi, and then of course the stereograde test also tests the coordinates, XY coordinates, to find out how they have transformed. Are you okay? Whether they are okay or not, then obviously the instrument is not good enough. So these are tests that are done in the last few pages, in this lecture, which we started last week. The monograde test, the stereograde test, and then we can talk about the other, checking the zero positioning of the dials, angular and linear dials, the faithfulness with which the instrument produce an undistorted model. Okay, so this is the new jollof. Are you okay? This is not Ghana jollof or Nigerian jollof. I told now about this, that this course just is a remix. It's like a remix. Are you okay? Just that I'm not going to write a song because people are not going to buy it. Okay, so it's something you know already that is being talked about in a very interesting way. Do you have any question per this first material? If you don't have any question, I think we still have 4 minutes to finish, with this. I think the other guy couldn't join us. It's a shame. I hope he doesn't write something that his own personal answers for me when the time comes for actually reach out for the next material, which I've actually put on your page. I think I have. So if you go for photo lecture 2, I don't know if you can see what I'm showing on the board. Okay. Right. Okay, so now this is the next topic. So once you understand the first chapter of what I'm actually talking about, which seem a bit complex. I don't know how you see it. For me, because I've been teaching it, it's always fun for me. But honestly, photogrammetry makes use of about 3 processes. So photogrammetry is nothing more than photographs. We want to measure from them. Now, you can't just measure from any photograph. It has to be the vertical photograph. Okay. So now the vertical photograph that you want to actually measure from, do you just get up and start measuring from it? No, you have to take it through a process. And the process, we don't say the process, we actually say an orientation, or the orientation process. Are you okay? So now the first orientation, or the 3 orientation processes, are actually what we call the, where's my whiteboard? I love the whiteboard. So let me go for the whiteboard. Not use Zoom. Zoom whiteboard, I'm not sure about Zoom whiteboard, so I prefer to go for my own whiteboard. Where is it? He's down here. Okay, great. So I would like to talk about 3 types of orientation. Let me see if I can use their tests. Okay, I can get it. The first one is IO, which is actually interior orientation. Interior orientation. Okay, the second one is relative orientation, arrow. Okay. Then the third one is absolute orientation, AO. And you see, these were mentioned in the stereograde test, but since you've not been told about it, how are you going to appreciate it? Okay. So thank God that, of course, I knew it, so I told you and I warned you about it. So there are 3 orientation processes in photogrammetry that you want to actually take, you know, the photographs, the stereo pairs through before you get to the end, and then you have the final product, which is really what you need. Your XYZ, you know, what is the essence? What is the moral? What is the idea behind doing this? The idea, and I'm going to be talking, I'll just be here and then we'll change